So this video is day 2 of our U-substitution stuff. So let's remind ourselves about how we do some U-sub. So we're going to take the integral of pi times the sine of pi x dx. Okay, so here we have a constant pi times a trig of pi x. So the first thing we have to decide is, what do we want to call u? And usually if we have trig, it's the stuff in your parentheses, your argument of trig. So we're going to call this your u value. U is going to be pi times x. Okay, because we want to solve and substitute so we don't have any x's in your problem anymore, but we all have u's. So the next step is to take the derivative of our u value. So pi times x, the derivative is just pi times dx. Because over here now we want to also replace dx so that we don't have any x's in our integral anymore. So we're going to solve this little thing for dx by dividing both sides by pi and getting a dx value of du over pi. Okay, and now we do some substitution. So we replace your after sine with u, right? We called pi x u, so that's the sine of u. And then dx we replace with du over pi. Okay, now hopefully things like this happen where the pi in front divides by the pi there, and we have a super simple integral, the integral of sine of u du. Okay, so sine is the antiderivative of, well, nothing but cosine has a derivative of negative sine, which means sine has an antiderivative of negative cosine of u, plus c. Okay, so once we get to here, we have to go back in and replace our u with what we defined it up above, and that was pi x. So our final step to doing this u substitution is to resubstitute in your u value from up above in order to get our equation with x once again. Some nice u substitution. Okay, let's try another trig one. How about the integral of 1 over theta squared times the cosine of 1 over theta d theta. 1 over theta squared, cosine of 1 over theta, d theta. And if you don't like thetas, make them all x's. Theta and x are variables. Theta is usually the variable for trig, but x also works. So we're going to go ahead and call this your u. U is 1 over theta. Okay, so when we take the derivative of 1 over theta, we are first going to convert this into a polynomial. So theta to the minus 1 power. Okay, rather than doing 1 over theta, we make it theta to the minus 1. So in our rules, we will subtract 1 from the exponent. And do we do anything else to it?
Oh, we bring up the... Oh, wait, we bring down the negative 1, right? Wouldn't it be negative theta?
Bring the negative theta to the front. So negative theta to the negative 2. Negative theta to the negative 2. That sounds good. D theta. So we need to solve this for d theta so that we can replace d theta here. So when I solve this for d theta, I get du over negative theta to the negative 2, which is the negative of theta squared du. So if we have a negative exponent in the denominator, which is what we have right here, a negative exponent in the denominator, it can come to the numerator as a positive. But the negative here still stays negative. That doesn't change. just because you went from bottom to top. Okay, so there is our substitution. So let's get to substituting. We have 1 over theta squared times the cosine of u times negative theta squared du. Okay, and this is a beautiful thing because the theta squared on the bottom can cancel out with the theta squared on the top. Okay, but we can't get rid of the negative. The negative stays there. So we're integrating negative cosine of u du.
Yeah, the negative goes to
The negative of cosine. So this is a negative 1 times, so not subtraction of cosine, but negative 1 times the cosine of u. So then what is the antiderivative of negative cosine? That will be negative sine. U, right, plus c. So then our last step is to go ahead and replace our u value once again. And u was 1 over theta. Plus c. And that should be that. Okay, let's look at one with an e in it. We haven't done any with e's yet, so let's see. 5 minus e to the x over e to the 2x dx. Okay? So hopefully you see that there is a subtraction sign on top, which means we're probably going to want to break this into 2 integrals and use the properties of integrals that can break it into the integral of one fraction minus the integral of the other fraction. Okay, so that's what our goal is going to be here, is to change this into 2 integrals. Okay, so there's a couple ways we can algebraicize this to begin with. Algebraicize is not a word, I know, but I want to say it anyway. So we're going to bring this up and multiply it by the e to the negative 2x. Okay, so I'm taking my e to the 2x from the denominator to the numerator so that I can distribute it into both of my parentheses here, my subtraction. So this is 5e to the minus 2x minus e. So now I have 1x, right? I have the like bases. So I'm going to add my exponents. So x minus 2x is negative x. So I have e, or 5e to the minus 2x minus e to the minus x. So now that I have a subtraction sign, I'm going to use the property of integrals and break this into 5e to the minus 2x dx minus the integral of e to the minus x dx. Okay, so this is the trick here that we want to employ in order to now have 2 separate u's. So we're going to pick a u value for this integral, and we're going to pick a u value for that integral. Okay, they do not have to be the same u's because they're 2 separate integrals. Okay, and that's the trick to doing this problem. Anytime we have a subtraction, you're going to split it into 2 so that we can make a better choice of our u's. So here, let's let u be negative 2x. Negative 2x. Okay, so then du is equal to negative 2 times dx, and dx is du over negative 2. And over here in this one, let's let u be negative 1x. So u is negative x, which makes du negative dx. So dx is negative of du. Okay, so we still employ those same steps in solving for dx so that we can replace dx here and we can replace dx over there and just have 2 equations with u in it. So that means I'm going to have 5e to the u power times du over negative 2 minus the integral of e to the u negative du. So remember, this is a negative du. Okay, so let's see, what do we have? I have a 5 and I have a negative 2, so I can pull that negative 5/2 outside of my integral and just have e to the u du. Right? I can pull this negative 1 out, making this a plus 1 integral of e to the u du.
Why is it plus now?
Okay, so the antiderivative of e to the u is just e to the u. So minus 5/2 e to the u. And over here, the antiderivative of e to the u is once again e to the u. And there's a plus symbol in between here and plus c. So then your last step is to come back here and replace each of your u's with their respective things from up above. So the yellow u was negative 2x. And the green u was negative x. Okay, so we take the antiderivative of this by splitting it into two separate functions, right, or two separate integrals, so that we can take two separate u values and that we can solve it all the way down to that. Okay, so let's see what happens when we have a definite integral and we have a lower bound and an upper bound. So we'll take the integral from negative 1 to 1 of x times x squared plus 1 cubed dx. Okay, so let's look at that one. We're going to use the same method of U-substitution in order to take the antiderivative of this product. Okay, so we're going to define this parenthesis thing, right? Only this stuff in here. This is going to be your u value for substitution. So we're calling u x squared plus 1. Okay, to simplify this equation a little bit before we antiderive. So if that is u, then du is 2x dx. Okay, and then solving this for dx gives you du over 2x. So now that I have chosen my u and I have solved it for dx, I can do my substituting. So the integral from negative 1 to 1 of x times u to the third power times du over 2x. Okay, now in each of these examples that we've done so far, and probably this whole entire time, all of the x's have canceled out. Okay? And it's been really nice because you only have u's in your problem. Now if the x's didn't cancel out, we would have to come up here to the way that we define u and solve this equation for x. Okay, we would solve this equation for x and then we would replace any x that we have with that u value. Okay, we haven't had to do any of those yet, but it's possible that you will have to do some in the future. So in case you run into that, that's how you handle it. So let's see, let's do some simplifying. We have the integral from negative 1 to 1 of 1/2 u cubed du. So now let's take the antiderivative of u cubed. Okay, because I'm going to pull this 1/2 out to the front and make it 1/2 times the integral of u cubed. Okay, perfectly normal and mathematically acceptable to do that. So what is the antiderivative of u to the third power? Well, that's u to the fourth divided by 4. Okay, because we add 1 to the power and we divide it by the new power. And we're going to evaluate that from negative 1 to 1. Okay, so what we're going to have to do, since we haven't changed our integration variables, is we're going to have to now go back in and replace u with how we defined it up above. And I believe we said u was x squared plus 1. So we still have dividing by 8, because that's what 2 times 4 is 8. And I'm going to raise this to the 4th power, and I'm evaluating it from -1 to 1. Okay, so when we get to here and you have your u value, once again we have to replace u with our x that we defined it up above. So if we're going to do this, that means we take 1 squared plus 1, raise it to the 4th power divided by 8, minus -1 squared plus 1 raised to the 4th power divided by 8. Okay, so 1 squared is 1. 1 plus 1 is 2. 2 raised to the 4th power is 16. 16 divided by 8 is 2. Minus -1 squared is 1. 1 plus 1 is 2. 2 to the 4th is 16. 16 divided by 8 is 2. And 2 minus 2 is 0. So that's the end. Now your assignment is to do all the problems from the worksheet that we didn't do in class. Okay, so practice your anti-differentiation and U-substitution.